Hello everyone, we are here to record Unit 3, Part 2. We are still talking about regular operation, deterministic and non-deterministic automata. We are still reading Sipser book and we are still in Chapter 1. I would like to remind you a non-deterministic model. Non-deterministic finite state machine is capable of being lucky. It can guess or to which state to jump or which input letter to use. For example, we can choose to move from one state to another state with epsilon transition without reading any input letters. Or if we have several possibilities, we can choose one of the possibility. Like here, we have a Q1 state and several possibilities to move with one to the state Q2 or to the state Q3. And sometimes we can have not defined transition. For example, here at the third drawing, Q1 on 0, the transition is not defined. The NFA model works in the following way. We have several possibilities as several computational paths. So we have a tree of possibilities. The roof of this tree is the starting state of our automaton. Each branch is multiple choices for our computation. To decide if the word belongs to our language or if the word belongs to the language of our automaton, we have to find at least one path that ends with an accepting state. To decide that the word doesn't belong to the language of the automaton, we have to check all the paths and we have to check that all the possible paths reject the word. Okay, we would like to ask ourselves a question. Does the DFA is more powerful than NFA? Or maybe NFA model is a more powerful model than DFA? What does it mean to be more or less powerful? So we will start talking in a moment about the subject. Basically, Mikhail Rabin and Dana, together with Dana Scott, started to talk about non-deterministic finite automaton as mathematical model, and later they actually proved that non-deterministic finite automaton is equivalent to deterministic finite automaton, and that is what we will do right now. The theorem I would like to prove is every NFA has an equivalent DFA. And once again, we are talking about the theorem of Dana Scott and Mikhail Rabin in 1959. First, let's start to define what is equivalence of finite automaton. I will give the following definition. Two automata are equivalent if they recognize the same language. For example, here in this example, we have two possibilities. We have automaton A with two states, and we have automaton B with three states. But the language of A is actually the same language as the language of the automaton B, and the language accepts all the words of odd length. So it doesn't matter if we use automaton A or automaton B, we will accept the same words and the language will be the same language. So how can we prove that DFA model equivalent to NFA model? We will start from an example. Let's see what is different in non-deterministic model. The difference, or the huge difference, is in transition function. For example, in some state Q, for an input letter alpha, we can have more than one transition. We can reach more than one state. For example, delta function of NFA from Q alpha equals to Qi, Qj, Qk states. The meaning of this transition is that the next state in NFA will be one of the several possibilities. So, if I want to build a DFA, I can't reach only one state. For example, for the state Q and input letter alpha, I should reach the state that actually is a union of Qi, Qj, and Qk. So basically, our proof idea will be to build a DFA equivalent to NFA, and we will use the transition function where we can move from one state to the new state, which is actually a union, a combination of several states. So basically, a delta function in deterministic finite automaton from Q and alpha, current state Q and input letter alpha, will equal to Qi, Qj, Qk as a state which actually is a set of three states. So let's analyze what happens if I want to analyze my two letters input. For example, from current state Q, where do we go on input alpha, beta? So on Q on alpha, we can reach Qi, Qj, Qk. For additional letter B, we have to check where we go from Qi on B, where we can move from Qj on B, where can we move from Qk on B, and then we have to unite the resulting state. So in formula, the next state of the equivalent DFA will be a set of all states that we can reach in NFA from current state and the next input letter. For example, delta cap Q alpha concatenation beta equals to delta Q alpha, all the states we can reach on reading alpha, comma beta. So first we will talk about delta of the state Qi, Qj, Qk on input beta, and it should be equals to the delta function with Qi on beta union delta function of Qj and beta union with delta function Qk in beta and beta, which will be Qj, Qm, Qn, and Qp in this current drawing. So let's define how we build an equivalent DFA for an NFA with no epsilon transition. Let A be an NFA that we will use, and it will be defined by its 5 tuple. We will construct a DFA M, and once again we have to give a 5 tuple for M definitions. And this DFA will be equivalent to A. So we will start with Q, a power set of QA. We will take a power set of all the states in QA, and this will be our new set of states. The alphabet will be the same alphabet, and for each state R in Q and each input letter sigma in sigma, we will define the transition delta R sigma as a union of all states small r in R such that delta A R sigma. So we will check where we reach for each R state and letter sigma in non-deterministic finite automaton, and we will unite all the results. The initial state Q0 will be the state Q0A, and the set F of a finite state will be all the sets R where at least one state is an accepting state. Therefore, R intersection FA is not an empty set. Let's visualize the definition of transition function. So we have a state R, which is built as a power set, as a partial set of states of the original automaton. Let's say that we have Qi, Qk, Ql states, and we would like to define the transition function delta for R and alpha. So we will check where we go from Qi and alpha, and we will check where we go from Qk and alpha, and we will check where we go from Ql and alpha. We will union all the resulting states, and we will have S as a resulting state. The S will be defined as an accepting state if at least one of the states in it is an accepting state. So let's see an example. For example, we are giving the following non-deterministic finite automaton without any epsilon transitions, and we are asked to transfer it to deterministic finite state automaton. So let's build together the solution for this automaton. For state Q0 and 1, we move to Q1. For state Q0 and 0, the transition is not defined, so we will move to a new state, an empty state, and we will stay here forever. For the state Q1 and 1, we should stay in Q1, and Q1, 0, we can or stay in Q1 or move to Q2. So on 0, we will move to double state Q1, Q2. In state Q1, Q2, we will move on 0 to the state Q1, Q2, Q3, because Q1 on 0 we can move Q1, Q2. Q2 on 0 we can also reach Q3. So Q1, Q2 on 0 we move to the state Q1, Q2, Q3. State Q1, Q2, Q3 on 0 we stay in the same state. Q1, Q2 on 1 we return to Q1. Q1, Q2, Q3 on 1 we return to Q1, Q2. The states Q1, Q2 is an accepting state, since Q2 is an accepting state. The state Q1, Q2, Q3 is an accepting state, since Q2 was an accepting state. So here we have the resulting deterministic finite state automaton. So let's try to understand what should we do with epsilon transitions. I would like to give additional definition. The epsilon closure of a state is a set of all states reachable from the current state using only epsilon transition. The notation is E on current state Q, and the result is a set of states, P belonging to the Q, such that delta cap Q epsilon star equals P. So we check where should we, which states can we reach only with epsilon transitions. So we can use epsilon star in power of star, and we combine all the results, and it will be an epsilon closure of the current state. So basically, I'm interested in, without moving in input, where can I jump? Which state can I reach? So I would like sometimes to use epsilon closure to understand how many more states I can reach without reading any input. Let's see an example. Here we are giving an automaton with 5 states. Please pay attention. The transition between Q2 and Q3 is with letter sigma, or all the rest of the transitions are epsilon transitions. Okay, let's compute epsilon closure of the state Q0. At the state Q0, without using any epsilon transition, I can stay in Q0. With one epsilon transition, I can move to Q1. With two epsilon transitions, I can reach Q2. So epsilon closure of Q0 is Q0, Q1, Q2. Okay, if I would like to analyze epsilon closure of Q1, it will be Q1 if I don't use any epsilon transitions, and it can be Q2 if I use one epsilon transition. Please pay attention that epsilon closure of Q2 is only Q2 because we don't have any epsilon transitions from this state. Okay, let's move to the state Q3. In the state Q3, epsilon closure is Q3 itself, and we also can reach Q4 with one epsilon transition. And epsilon closure of Q4 is Q4 itself. So let's try to define DFA equivalent to NFA with epsilon transitions. So let's assume that we are giving some non-deterministic finite automaton A, and we have its 5 tuple, and we would like to construct a DFA-M, once again a 5 tuple, equivalent to A. So once again, we will start from Q as a power set of QA. The alphabet will be the same alphabet, and here we will have some changes. For each state R of DFA and input letter sigma, if we would like to know the delta function of R and sigma, we will compute delta A function of for each state small letter R and sigma, and then we also will use epsilon closure for this computation, and we will unite all the results together. Additional difference is the starting state. Since we can have epsilon transitions now, the starting state may be not the single state. Maybe from the starting state with epsilon transition, I can reach additional states. So the new starting state is a epsilon closure of Q0A. And the set F is defined in the same way. The state F, we have all the states R in Q, such that at least one state in the set R is an accepting state. Therefore, R intersection FA is not an empty state. Okay, let's visualize our computation. Once again, given delta function for the state R, which is a state that has Qi, Qk, and Ql in it, and we would like to compute delta function on input alpha, we compute where can we go from Qi and alpha, Qk and alpha, Qj and Ql and alpha. But now when we reach the states, we also use epsilon transition. Let's say that we have an epsilon transition from Qm to some Qb state and Qs to some Qa state. So we add Qb and Qa to our resulting state. So we also add epsilon movement where we can move without reading any input. Okay, so let's try to solve an example. We are giving a new automaton with two epsilon transition from Q0 to Q1 and from Q1 to Q2. And we are asked to transform or to build an equivalent deterministic finite state automaton. Once again, I advise you to stop the lecture recording and to try to solve this question by yourself. The solution will be the following solution. We start with a state that is epsilon closure of Q0, and the state will be Q0, Q1, Q2. This state is an accepting since Q2 is an accepting state. Now we will compute where do we go for an input 0. For an input 0, we can stay in Q0, but we can also move with epsilon transition to Q1, Q2, and use 0, so we can also reach Q2. We can use epsilon, we can use 0 epsilon and reach Q1. We can use epsilon, epsilon and 0 to reach Q3. Therefore, from the state Q0, Q1, Q2 on input 0, we can reach states Q0, Q1, Q2, Q3. And the state is an accepting state since Q2 is an accepting state. On input 1, we move to the state Q1, Q2. Q0 on 1, we don't have a transition, but we can use an epsilon transition to move to Q1, and with 1 we can stay there. And we also can use epsilon 1 epsilon to reach Q2. Now let's analyze what do we have in Q1, Q2 on input 1. Q1, Q2 on input Y, it's a self loop. We stay in Q1, Q2. Q0, Q1, Q2, Q3 on input 0, we stay at the same state, so it's a self loop. Q0, Q1, Q2, Q3 on input 1, we can reach Q1 and Q2. Since we don't have any transition with 1 for the states Q2 and Q3, so basically our computation, the computation that uses ones is actually the computation for the states Q0, Q1, since Q2 and Q3 don't have any transitions with 1 or with epsilon. Okay, Q1, Q2 on input 0, we can reach Q2 and Q3. Q1 on 0, we can use epsilon 0 and reach Q2. But we can also use epsilon 0 and reach Q3. The state is an accepting state since Q2 is an accepting state. Okay, Q2, Q3 on 0, we return to Q0, Q1, Q2, Q3. Q1, Q3 on 1, since it is not defined, gives us an empty state, a trap state, and here we stay forever. I hope that you have the same solution, the same drawing as I have. Okay, so let's return to our sentence, our theorem. Every NFA has an equivalent DFA. The proof idea is that we construct the automaton that is exactly the same or accepts exactly the same language. We will use the algorithms we saw before. If NFA without epsilon transition, we will use the first algorithm for construction. If our NFA has epsilon transitions, we will use the second algorithm that we use for construction of DFA. The automaton that we managed to build is a deterministic automaton equivalent to A. We will prove it in a moment. Therefore, a conclusion is a language is regular if and only if some NFA recognizes it. We talked about it during our practical exercises. Somebody asked me, what is the meaning of regular language? And I told you that if you can manage a non-deterministic finite automaton or deterministic finite automaton that accepts the language, then your language is a regular language. Therefore, if I would like to prove that some language is regular, I can build DFA or I can build NFA, since I can prove that for each NFA I have, I can build an equivalent DFA. Therefore, from our point of view, it doesn't matter which model we will use to prove the regularity. We can use deterministic finite automaton or non-deterministic finite automaton. Okay, so let's start the formal proof of our construction. We suggested a conversion of NFA into a DFA-M in the way we saw before. So now we need to show that the language LM equals to the language of A. LM equals LA. So we will show that for each word W that belongs to sigma star, delta cap A epsilon closure Q0AW is actually equals to delta cap N QSW. And we will use induction on word length as our proof method. And the proof will be in our next slide. Before moving to the languages, let's first prove that transition function of automaton A and transition function of the automaton M will reach the same states on the word W. So instead of writing epsilon closure of Q0A, we will write QS. This is a substitution in our notation. Induction basis. Let's look at the word W of the length 1, and it has a single letter. According to what we did, or according to our construction, delta cap A QS sigma equals, by definition of NFA, to union of R that belongs to QS of transition function delta A of the state R on the letter sigma, and we will have an epsilon closure. We have a parenthesis missing in this equation. By definition of delta cap function of the automaton M, what we had in our equation, the union, the result of the union is the definition of delta cap M function for the state QS on the letter sigma. So the basis of the induction is proven. Induction hypothesis. We will assume that the theorem is true for any word W with the length less than n. And the induction hypothesis is that delta cap A QSW equals delta cap M QSW. So we can reach the same state. Now we will show that the theorem is true for the word W with an addition of single letter sigma. Okay, so we will start. Delta cap A QS W sigma, concatenation with sigma, equals to the union of all the states R that belong to delta cap A QSW, such that delta A R sigma epsilon closure, we do an epsilon closure and we have a union for each state. So let's see what we did. First, we looked to which states we can reach on reading only input W. Then we added additional letter sigma, and we also computed an epsilon closure of this. By hypothesis, we know that this part of the equation equals to the union of R that belongs to, let's see, here is the change, delta cap M QSW and epsilon closure of the state of the states delta A R sigma. So once again, we will use now deterministic model. We will see where we can reach from the starting state on reading the word W, which states we can reach. Then we pick each state and we see where we can reach with only one letter sigma and epsilon closure, and we unite all the results. By definition of delta function of the automaton M, this part of the equation equals to delta M, delta cap M QSW sigma. So according to the definition, it is the states that we can reach or using extending transition function on reading the word W and an addition of the single letter. And this is equals to delta cap M QSW sigma by definition of delta cap function of the DFA. Okay, now the next state. We will prove that the language of M equals to the language of A. We will prove this theorem by using bidirectional inclusion. So we will start with the word W belonging to LA, to the language of non-deterministic finite automaton. Delta cap A QSW equals to P, and P is an accepting state. P intersection FA is not empty. By using the previous theorem, we can replace delta cap A with delta cap M. Therefore, delta cap M QSW equals P, and P belongs to F according to the definition of the F set of the automaton M. And that means that the word W also belongs to LM. That's it. That's how we prove that LM equals to LA. Okay, let's go back to the concatenation. Finally, it took us almost 2 weeks. So I would like to remind you the theorem. If L1 and L2 are regular languages, therefore L1 concatenation L2 is also regular. Now we will prove this theorem by constructing a correct automaton, and we will use non-determinism. Okay, let's assume that we have an automaton M hat that accepts the language L1, and we have its 5 tuple. Let's assume that we have an automaton M2 that recognizes L2, and once again we have its 5 tuple. And now let's construct an automaton M that recognizes L1 concatenation L2, and we will define its 5 tuple in a moment. The meaning of the concatenation: we read some prefix in automaton M1, and then we want to move and to continue to read some suffix in automaton M2. Basically, the whole idea of the concatenation. So we will build a new automaton that will be a combination of 2 previous automaton. So the new automaton M will have the following 5 tuple. We will have the union of the states in Q1 and in Q2. The sigma will be the same sigma. The starting state QS will be Q01, the starting state of the first automaton M1. And the final set will be only the final set of the second language, L2, therefore F equals to F2. We will keep all the transition functions that we had in previous automatas, but with addition of epsilon transition from final states of the automaton M1 to the starting state of the automaton M2. Therefore, delta function equals delta 1 union delta 2 union. For each state Q in F1, we have a transition function delta Q epsilon equals Q02. M will start reading the word on simulation and simulating it in automaton M1 for a while. After reaching some accepting state in M1, we can move without reading any input to the initial state of the automaton M2. And then M can simulate the rest, the suffix of the word in M2. If after choosing all the passes, we manage to reach an accepting state, the word belongs to the concatenation language. And if after checking all the possibilities of prefix and suffix, we can't reach an accepting state, then the word should be rejected by automaton. Okay, let's see the following example. we will consider the concatenation of the language 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1 with language of odd number of zeros. 0, 3 zeros, 5 zeros, and so on. We will do this exercise during the practice hours, and we will draw an NFA for the language L1 concatenation L2. Let's talk about how do you prove that the construction of concatenation non-deterministic finite automaton is correct. We would like to prove that the language of M equals to the language of M1 concatenation M2. The basic idea of proof is the following one. We will take the word W that belongs to sigma star. Then we will compute the delta cap function from QSW, and we will get Q, some state that is finite. And we can reach a finite state if and only if we can divide W on prefix U and suffix V in such a way that prefix U, when we start reading it in automaton M1, in the state Q01 on U, we will reach some state P, which be a finite state of the automaton M1. And then we will move and continue our reading of the suffix V, and we will start it by reading at the state Q02 on V, and we will reach some state Q, which will be an accepting state of F2. Therefore, we can prove that M accepts W if and only if M accepts the prefix U and M2 accepts the suffix V. Okay, we already proved that union is a regular operation, or more correctly, two regular languages. The union of two regular languages is still a regular language. But we use a Cartesian product automaton, which is a little bit difficult to construct. We can use as a non-deterministic automaton to prove that the union of two regular languages is also a regular language. Let's assume that we have a language L1 and automaton M1 that accepts it, and we have its 5 tuple. Let's assume that we have language L2 and automaton M2 which accepts it. Now we will construct automaton M, which is a union of L1 and L2, but this time we will use non-deterministic finite automaton, and we will define its 5 tuple in a moment. I advise you to stop the recording and to try to think about additional way how you can construct the union of two languages, how you can construct a new automaton M from the automaton M1 of the language L1 and automaton M2 of the language L2. Okay, we know that the word belongs to the union if it's belong or to language L1 or to the language L2 or to the both of them. That means if we will start reading the word in automaton M and reach the final state, accepting state, it's a good. Or if we will start reading the word from the state Q02, or initial state of the automaton M2, and we will reach a finite state, it's good. So we will choose non-determinism to guess to which automaton to go, which automaton to use, M1 or M2. And our solution will be relatively simple. We will build a new automaton, which will be the combination of two previous automatons, but we will add one new state, Q0, and two epsilon transitions. The transition, which will be the jump to the initial state of the automaton M1, epsilon transition, and transition, which will guess that we should go to automaton M2. So we have a transition from Q0 with epsilon to Q02. Okay, the formal definition of 5 tuples that we are using. Q will be a union of Q1 with Q2 and with additional state Q0. Alphabet, sigma will be the same alphabet. Transition function. We will keep all the transition function of M1, delta 1. Union with delta 2, we will keep all the transition function of delta 2. Union with two transitions. We will have delta Q0 epsilon moving to Q01 and to Q02. Q0, the state that we added, will be the initial states, and the set of final states will be the union of F1 and F2. Once again, if you want to prove or to give a formal proof that our construction was correct, so we want to prove that Lm equals to Lm1 union Lm2. The basic idea will be if we will take the word W belonging to sigma star, then delta cap Q0W equals to Q for some state Q that belongs to F, if and only if either delta cap Q01W equals Q, and Q is an accepting state, Q belongs to F1, or delta cap Q02W equals Q for some Q, which is an accepting state of the second automaton F2. Hence, W accepts W. Hence, M accepts W if and only if M1 accepts W or M2 accepts W. That's basically the idea of our proof. Okay, additional operation and additional theorem. If L is regular, then L star is also regular. We want to prove that Kleene closure or start operation is closed under regular family. So we will take M, the automaton that recognizes some language L1, and we will have its 5 tuple, and we will construct a new automaton M such that the language of M will be L1 in power of star. So Kleene closure of L1. Once again, I advise you to stop the slides and to think how can we draw a new automaton for Kleene closure operation. Okay, the Kleene star closure. The idea of Kleene star is that we have a concatenation of the language L1 with itself. So after reading the word, some part of the word, and reaching the finite state, we can jump and we can assume that we move to the concatenation. So we will read the next part of the word and reaching the final state. Once again, we want to return to the initial state. So therefore, we have epsilon transition for each finite state, accepting state of the automaton M1 to the state Q01. But please pay attention. The first initial state, Q01, not always an accepting state. And in Kleene star operation, an empty word epsilon always a member of the resulting language. Therefore, we will add additional QS initial state, and it will be accepting state. And then we will have an epsilon transition to the state Q01 of the previous automaton. This way, our 5 tuple will be, our set Q will be Q1 union QS, this new state. The alphabet will be the same alphabet. The starting state will be our new state QS. The final state will be, the final set state will be F1 with union with QS. Since the initial state is now an accepting state, we decided to accept an empty word. Transition function, we will keep all the transition of our automaton, delta 1, union Okay, we have several transitions that we add. The first transition is simple. Delta QS epsilon to Q01, the jump from initial state of new automaton to initial state of the old automaton. And also for each Q in F1, we will have a transition, an epsilon transition function, delta Q epsilon equals to Q01. This will be our automaton for Kleene star closure. You will have your homework task to prove that this construction is a correct construction. That the language of LM equals to L1 star. Basically, you should do the following proof. You should take the word W that belongs to L1 star. Then you have to assume that there is such K that W belongs to L1 in power of K. Then you have to divide the word W to K parts. And if W belongs to Lm, then its process ends in some kind of state F, and you have K times visiting different accepting states in F, and then returning to Q01. Once again, reaching an accepting state and return back. This will be your home task to prove that this construction that we did before is a correct construction. Okay, additional exercises that we will solve together during our practice meeting, our Zoom meeting, giving the following non-deterministic finite automaton. We will be asked to build an equivalent deterministic finite automaton. That is the end of Union 3. We finished about non-deterministic finite automaton, and we will meet during our practice exercises Zoom meeting. And next week we will start the new topic.